Good morning. Today we will study disconnectedness in topological space. So first of all, we will study one result related to homomorphism. In previous lecture we studied about homomorphism in detail. So homomorphism is an equivalence relation in the collection of all topological space. So to prove it is an equivalence relation, we will show that homomorphism is a reflexive relation, it is symmetric relation, and it is transitive relation. So first of all, we know that if Xt is a topological space, then Xt is homomorphic to Xt. So homomorphism is a reflexive relation. Now suppose Xt is homomorphic, topological space Xt is homomorphic to a topological space YU. Y is a non-empty subset and U is a topology defined on Y. Here X is a non-empty set and T is a topology defined on X. So together Xt is a topological space and YU is a topological space and Xt is homomorphic to YU. Then there exists a homomorphism F from Xt to YU. So by definition of homomorphism, it means that this F is 1, 1 and onto. Secondly, F is TU continuous and F inverse is UT continuous. So it means F inverse is a homomorphism from YU onto Xt because F is 1, 1 and onto by 1, it means F inverse is also 1, 1 and onto. By third, we know that F inverse is a UT continuous and from 2 F is TU continuous. F is nothing but inverse of F inverse. So second F inverse is UT continuous by 3 and F inverse of inverse is F, it is TU continuous by 2. So it means topological space YU is homomorphic to topological space Xt. So we have shown that if Xt is a homomorphic to YU, then YU is homomorphic to Xt. Now transitive. Suppose Xt is homomorphic to YU and YU is homomorphic to ZW. Here Z is a non-empty set and W is a topology defined on Z. Suppose F is a homomorphism on topological space X2 to YU and G is a homomorphism from a topological space YU to ZW. Now we will show that topological space Xt is homomorphic to topological space ZW. We observe that G of F means composition mapping of G and F is a homomorphism from X to Z. Why this is true? Because we know that because F is a homomorphism, it is 1, 1 and onto. And G is also a homomorphism, so G is 1, 1 and onto. If F is 1, 1 and onto and G is 1, 1 and onto, then G of F is also 1, 1 and onto. By definition of homomorphism, F is TU continuous. Also because G is homomorphism, G is UW continuous. It means G of F is TW continuous. Also because G is a homomorphism, F is a homomorphism, therefore G inverse is WU continuous and F inverse is UT continuous. It means F inverse of G inverse is WT continuous and this implies G of F inverse is WT continuous because G of F inverse is F inverse of G inverse. So we have shown that homomorphism is reflexive, it is symmetric and transitive. It means homomorphism is an equivalence relation in the collection of all topological spaces. Now separated set. Let A and B be subsets of a topological space Xt. Then the set A and B are said to be separated if and only if A is not equal to phi, means A is non-empty and B is non-empty. A intersection with B bar is empty. A bar intersection B is empty. Means A and closure of B are disjoint and closure of A and B are disjoint, where A and B are non-empty sets. Suppose we consider the usual topology U on R and the subsets A equal to 2, 3, in B equal to 3 to 4 and C equal to closed interval 4 to 5. These are open intervals and this is closed interval. We notice that A and B are separated sets. Why? Because A is non-empty and B is non-empty and A intersection B bar means closure of B. A is the open interval 2, 3. Closure of B is closed interval 3 to 4. So intersection of open interval 2 to 3 with closed interval 3 to 4 is empty set, means these are disjoint. Also closure of A intersection B, closure of A is closed interval 2, 3, intersection open interval 3, 4 is again empty set, means closure of A and B are disjoint. So it means A and B are separated sets. But B and C are not separated set. Why? Because here B and C are non-empty, but closure of B is closed interval 3 to 4 and C is 4 to 5. So their intersection will come out to be singleton set 4. It is not 0. Means closure of B and C are not disjoint. So it means B and C are not separated. Now disconnectedness. Let Xt be a topological space and A is a subset of X. The set A is said to be disconnected subset of X if there exists G and H belonging to T, means G and H are open sets in T such that number 1, A and G are disjoint, A and H are disjoint. Secondly, A intersection G intersection A intersection G, H is a empty set and A is equal to A intersection G union A intersection H. If all the three conditions are satisfied, wherefore G and H, where G and H are elements of T, means they are open sets, then we say that A is disconnected or separated subset of X. And in this case, G union H is called a disconnection of A. And the set A is connected if and only if it is not disconnected. If we replace this A by X in this definition, then it becomes replace A by X. X and G are not equal to phi, X and X intersection G is not equal to phi, X intersection H is not equal to phi, that is G and H are non-empty, are not equal to phi, and G and H, G intersection H is equal to phi, means G and H are disjoint, and X is equal to, here replace A by X, X intersection G union X intersection H. It means this is equal to G union H. Here G union H is a disconnection of X. So the set X is connected if it is disconnected. Now connected and disconnected spaces. The topological space Xt is said to be disconnected if and only if there exist open sets G and H belonging to T such that G and H are non-empty and G and H, intersection of G and H is empty, means they are disjoint. Also X is equal to G union H. So if all these conditions are satisfied, X is said to be disconnected. And X is said to be connected if it is not, if and only if it is not disconnected. So X is disconnected means X is the union of two non-void open subsets G and H that are disjoint. Non-void means they are non-empty and disjoint means their intersection is empty. When this happens, the pair, here it is G and H, the pair G and H disconnects X. Here it is not U and V, this is G and H. In this case, we say the pair G and H disconnects X. Now the component. A subset B of a topological space Xt is called a component of X if it is maximal connected subset of X. Now we will prove one result. A topological space X is disconnected if and only if there exists a non-empty proper subset of X which is both open as well as closed in X. Suppose A is a non-empty proper subset of X which is both open and closed. Now we will show that X is disconnected. Suppose B is equal to A complement. Then B is non-empty because A is proper subset of X. Here it is given to us non-empty proper subset of X. So therefore B is non-empty. B is complement of A. Also A union B is equal to X and A intersection B is equal to phi. Since A is both closed and open, it is given to us B is also both closed and open. Hence, closure of A is A and closure of B is B. And this implies that intersection of A with B closure is equal to phi. Thus, X has been expressed as the union of two separated sets and so X is disconnected. We have expressed X as a union of two separated sets. X is equal to A union B and A intersection B is phi. Now the converse part. Let X be disconnected. Now we will show that there exists a non-empty proper subset of X which is both open and closed in X. So we have assumed X to be disconnected. So by definition of disconnectedness, there exist non-empty subsets A and B of X such that A intersection B bar is equal to phi and A bar intersection B equal to phi. A bar is closure of A, B bar is closure of B and A union B is equal to X. Because A is always a subset of its closure and A bar intersection B is equal to phi, this implies A intersection B is equal to phi. It means A is equal to B complement. Because B is non-empty, it is given to us by definition of disconnectedness, B is non-empty and B union B complement is X. It means B is equal to A complement and it is a proper subset of X. Now X is equal to A union B bar is equal to X. Also A intersection B bar is phi. This implies A is equal to complement of B bar. Similarly, B is equal to complement of A bar. Since B bar and A bar are closed sets, it means A and B are open sets. Since A is equal to B complement, A is also closed. Thus, A is non-empty proper subset of X, which is both open and closed. We have also shown incidentally that B is also a non-empty proper subset of X, which is both open as well as closed. Now, local connected space. A topological space X is said to be locally connected if every point admits a neighborhood basis consisting of open connected sets. Suppose if we consider this diagram, and this is a point P, and this is a set V in the neighborhood of P. So in this, and this is a topological space. So in this topological space, V is a neighborhood of P, and it contains a connected open set. This one, the dark portion, this contains a connected open set that contains P. So a topological space X is said to be locally connected at a point X if for every neighborhood U of X there exists a connected neighborhood V of X such that V is a subset of U. Or more formally, if X is a topological space and X is a point in X, then X is locally connected at X if for every open set U containing X there exists an open connected set V such that X belongs to V, which is a subset of U. So the notion of local connectedness is useful in understanding the local behavior of a topological space. Now one last result. The subset of a topological space is connected if and only if it is connected in relative topology. We have studied relative topology in previous lectures. So if this it contains two parts. One is, if a topological space is connected, then it is connected in relative topology, and if a topological space is connected in a relative topology, then it is a connected space. So first one is which we prove, if the subset is connected, then it is connected in the relative topology. Suppose X is a topological space and Y be a connected subset of X, and U be a relative topology on Y induced by the topology T on X. Now we will show that Y is connected in U. Suppose if possible Y is not connected in U. If Y is not connected in U, then there exist open sets A and B in U such that Y is equal to A union B and A intersection B is equal to phi. And by the definition of relative topology, there exists open set GA and GB in T such that A is equal to GA intersection Y and B is equal to GB intersection Y. This is by the definition of relative topology. Now consider the set C, which is equal to GA intersection Y and D equal to GB intersection Y. Here GA and GB are open in X and C and D are open in Y. Also Y is equal to C union D and C intersection D is equal to phi, means C and D are disjoint. So this contradicts the assumption that Y is connected. Therefore, if Y is connected, it must be connected in the relative topology U. Now the converse part, if the subset is connected in the relative topology, then it is connected. Now let X be a topological space and Y be a subset of X, and U be the relative topology on Y induced by the topology T on X. If Y is connected in U, then it is connected. Suppose, if possible, Y is not connected. Then there exist open sets A and B in X such that Y is equal to A union B and A intersection B equal to phi. And by definition of relative topology, A intersection Y and B intersection Y are open in Y, and Y is equal to A intersection Y union B intersection Y. So this contradicts the assumption that Y is connected in U. It means if the subset is connected in the relative topology, then it is connected. Thank you.